So welcome back everyone to the second session of today. The first speaker will be Patrick Jefferson from MIT, and he will tell us about chiral indices and resolution independent structures in 4D F-theory vacua. Go ahead, Patrick.
Thank you, Ling. Thank you very much for the introduction. And I'd also like to give a very big thank you to the organizers of this conference for both organizing the conference itself and inviting me to speak. So today, sorry, I want to make sure the changing slides is working properly. Okay, good. Today, I'll discuss some upcoming work I should emphasize with Waddy Taylor, who's in the audience today, and Andrew Turner, I think, who may also be here. The subject of my talk today will be some recent work on analyzing F-theory compactifications on elliptic Calabi-Yau fourfolds with flux. These compactifications are described at low energies by 4D n=1 supergravity, and the inclusion of a non-trivial flux background permits a chiral excess in some cases, meaning a non-zero difference between the number of chiral and antichiral multiplets transforming in some representation R, and respectively complex conjugate of R, which I denote by R star of a 4D gauge group. So some motivations for studying these constructions are the following. One of the very first things we thought about at the initial stages of this project was analyzing the chiral spectrum of the so-called universal SU3 times SU2 times U1 mod Z6 model, which was described by two papers in 2019. And this is believed to be the broadest class of F-theory models with generic matter. Generic has a technical definition, which I won't go into for the sake of time here. But it is believed to be the largest class of models with generic matter, and this particular gauge group, the standard model gauge group with a Z6 quotient, which has been tuned in the geometric background. These models include, as a very special case, the so-called F11 model, which was shown to admit a quadrillion standard model chiral spectra. So this is one of the motivations, namely to analyze the chiral spectrum, or the possible chiral spectra of this class of models. A second broader motivation, I would say, is to study the difference between the landscape versus the swampland in the context of F-theory compactifications. That is to say, to try and answer the question, what set of F-theory, what set of 4D n=1 anomaly-free theories can be UV completed in F-theory? So these are two broad motivations for studying these constructions. Let me just give an overview of my results before jumping into details. What I'll discuss today entails, or I should say includes, a new approach to analyzing flux compactifications, which combines various techniques that have appeared throughout the literature in various places, along with a less explored mathematical characterization of the problem of studying flux compactifications. And what I hope to convince you of today is that there is something to be gained by revisiting what is, by all appearances, a very thoroughly studied problem. So I want to emphasize many of the techniques and actual computational methods that I'll discuss today are things that have appeared in the literature before, as this problem has received a lot of attention over the years. But the point is not so much to emphasize the discovery of new techniques so much as it is combining the techniques with a certain mathematical perspective, which will allow us to infer additional results and gain deeper insight into the nature of this problem. I should also say, before going any further, that there are a large number of people who have contributed research in the form of papers to aspects of this problem. And I unfortunately probably will not successfully cite everyone. I'm sure many of you are in the audience today, so let me apologize in advance for anybody who I failed to cite. I'll do my best, of course, to mention references where appropriate, but I don't think I'll be able to be exhaustive in that sense. So apologies in advance, and please let me know if I have overlooked a reference that is relevant to my discussion today. So continuing with my brief overview of the results, one of the results I'll discuss, of course, is this combination of computational methods. really the meat of this discussion includes, it involves combining the computation of topological intersection numbers via push-forward formulas and matching these intersection numbers with one-loop exact Chern-Simons couplings. So this, as I'll discuss in more detail, it leads to a very nice and powerful algorithm for computing chiral indices in the context of 4D F-theory compactifications. And then what it's allowed us to do rather easily, I have to add, is to compute vertical fluxes and chiral indices for a large number of F-theory models over arbitrary smooth threefold bases, which I denote by B. And one aspect of the emerging picture of the landscape that we're starting to see is that there is a lot of evidence that the given F-theory model with gauge symmetry G and matter representations R realizes all anomaly-free combinations of chiral matter. The second aspect that I'll discuss today is what is a relatively less explored mathematical characterization of the problem, in which we view the flux backgrounds as belonging to vertical flux backgrounds, specifically as belonging to a lattice, which I denote by lambda. And by lattice, I mean an abelian group, which is equipped with a symmetric bilinear pairing, which I denote by M. And in particular, this is an integral lattice. And what I will try to convince you of today is that there is a lot of evidence, enough so that we feel somewhat comfortable making a conjecture that this lattice lambda, whose non-degenerate part is isomorphic to a particular homology subgroup for smooth elliptic Calabi-Yau fourfolds, is resolution independent. And the resolution independence of lambda, I will try to explain, may facilitate more complete explorations of F-theory flux vacua in the future. So this, to us, looks like the most exciting result. I could linger on some of the specific details of the computations, but I think the more important point to emphasize in the short amount of time that I have today is that there is some evidence of a mathematical structure which is resolution independent, which may lead the way forward on future explorations of flux vacua in F-theory. So let me start by describing the basic setup. I'm going to consider F-theory on a singular elliptically fibered Calabi-Yau fourfold, which I denote by X naught. This is elliptically fibered over a base B, which is a smooth Kähler threefold, excuse me. And this construction can be described canonically by a Weierstrass model with this particular equation. This is, for our purposes, you can think of this as a hypersurface inside of some projective ambient space. And I'm going to focus my attention on F-theory models with gauge group G, some collection of charged matter, and a non-trivial flux background. So here's a very crude picture of the type of setup I'll be describing today. In this cartoon, this sort of flat blue plane, which is, I apologize for the crudeness of the picture. Obviously, this should have some curvature associated to it, but in any case, this is supposed to denote the base of the fibration, and these red circles are the elliptic fibers, which have singular points or develop singular points over particular subloci inside of the base. As usual, we'll play the game of sidestepping the fact that the compactification space is singular by computing what's called a resolution of singularities, where in the F-theory background, we compactify in a circle and we switch on gauge Lonomies for the 7 brane gauge fields, which allows us to move on to a generic point of the Coulomb branch and thereby resolve these singularities. So in practice, what we'll actually work with is a smooth sum choice, and it's not a unique choice, I have to stress, some non-unique choice of a smooth elliptically fibered Calabi-Yau fourfold X, which resolves the singularities of X naught. This resolution from a stringy point of view can be viewed as moving on to a generic point of the Kähler moduli space of X. We then use duality with M-theory compactified on X, and the flux background under this duality maps to a non-trivial background G4 for the M-theory flux G4. And so in practice, what we actually end up doing is, rather than starting with the geometry of the singular elliptically fibered Calabi-Yau background in the F-theory frame, we actually work with what you might think of as an ansatz for a flux background in the M-theory frame, and we determine the chiral spectrum from the geometry of X. So here's a very crude picture of the resolution of singularities. If one of the singular or a collection of the singular fibers rather has a singular point, we can do blowups, which replace the singular points with smooth spaces. In this case, a genus zero curve, or you can think of this as a complex projective space. Now, when talking about M-theory compactifications on Calabi-Yau fourfolds with flux, there's a number of consistency conditions one has to consider for the flux background itself. And these have been studied extensively over the past 20 to 30 years. I'm not going to dwell too much on some of the more subtle ones, which deal with the quantization of the periods of the G4 flux. Rather, I'm just going to focus today on the condition, one of the conditions that's necessary to preserve supersymmetry, which requires, well, it entails minimizing the Gukov-Laffa-Witten superpotential and so-called twisted superpotential. And one of the upshots of minimizing this sum of potentials is that G is forced to live inside of the 2,2 cohomology subgroup, which I'll denote by H upper 2,2. And for simplification, I'm further going to assume that G4 lives in a subgroup of H22 called the vertical subgroup, which is generated by, in this case, I'm going to be exclusively taking integer linear combinations. So it's generated by integer linear combinations of harmonic 1,1 forms, which I denote by the Poincare dual of divisors, D sub I. D sub I are divisors, or you might think of these as smooth or holomorphic 6 cycles inside of it, living inside of X, the Calabi-Yau fourfold. The vertical fluxes are then given by the integral of G4 over the classes of the intersections of these divisors. And these guys live inside of the homology, vertical homology subgroup, H2, lower 2,2. So what I've described so far is the basic structure one needs to think about when studying flux compactifications in M theory. However, this is not enough to necessarily ensure that a given flux background in M theory will lift to an F theory flux background. To ensure that this happens, one has, of course, has to take X to be elliptically fibered. By doing so, this implies that X will have a canonical basis of divisors. And in terms of this basis of divisors, it's possible to specify conditions that are necessary, and in this case, sufficient for the flux background to lift to a good, well-defined F-theory flux background that preserves diffeomorphism symmetry and the gauge symmetries that we desire to see in the at lower energies in 4D. So these are the conditions right here. And in terms of the structure, these so-called vertical classes, we can think of the chiral indices as being given as by integrals of G4 over these guys, rather a special subset of these homology classes, which are called matter surfaces. And they can be given by some appropriate linear expansion in the basis of 2,2 cycles. So the chiral index ultimately will be specified as some integral of G4 over the special subset of cycles. Now, it's possible to use intersection theory, for example, to evaluate the intersection pairing between G4 and any of these basis elements. So I'm being a bit sloppy with notation here, but what this equation is meant to express is that it's possible to evaluate these integrals in terms of some pairing, which can in turn be interpreted as a linear combination of intersection products between the classes of divisors and what's called the Schau ring. It's this basically the ring of intersections of appropriately defined objects that will tell us something about the signed or oriented intersections of the classes of divisors inside of the Calabi-Yau fourfold. And this can be computed using push-forward formulas that have been received a lot of attention and have been developed quite well over the years. So this is something that I'll come back to, but the nice idea is that if there's given the fact that X is taken to be elliptically fibered over the base, there's a canonical projection to the base that I'll denote by pi. And the push forward of this map, pi applied to the intersection products, can be used to re-express these quadruple intersection products in terms of linear combinations of triple intersections in the base. So if we know, for example, an explicit expression for the matter surfaces, then we're done. If we don't know an explicit expression, there's workarounds that people have developed. One of them is to compare to low energy 3D physics, where we match the fluxes or a collection of the fluxes to one loop exact 3D Chern-Simons terms. And this gives us linear combinations of the chiral indices. And as a linear system, we can invert the system to figure out how to express the chiral indices in terms of linear combinations of these 3D Chern-Simons terms, which are then set to be equivalent to the geometrically computed fluxes. So there's a couple different methods that one can use to compute chiral indices of these theories. So here's an example. Some of these results have appeared in the literature already, while some of them are new. We can look at so-called simple tape models in F-theory with simple gauge group. We start with the long form of the Weierstrass equation, and we can tune gauge symmetry on 7 branes that are wrapping a particular codimension 1 subset of the base by enforcing a particular order of vanishing for each of these parameters, A sub S, appearing in the Weierstrass equation. So here's a table of results for various simple gauge groups. And one of the interesting and perhaps satisfying results that we observe from looking at all of these different examples is that the constraints that we find on the chiral indices agree completely with Fourier anomaly cancellation. Another example, which will appear in forthcoming work with Wadi and with Andrew, is the chiral spectrum of the SU3 times SU2 times U1 mod Z6 model. This model contains the matter as its matter representations, the minimal supersymmetric standard model representations, and in addition, 3 exotic representations. We can realize the singular version of this model as a general cubic in P2. And then we can do some resolution to find a smooth geometry and compute the chiral indices according to the methods described above. Again, Fourier anomaly cancellation permits some particular set of combinations of chiral excesses in the theory. And it turns out that F-theory realizes all 3 families of these anomaly consistent combinations of chiral matter over generic base. So I want to stress also that the result on the previous slide for the tape models also applies over well, actually this is over an arbitrary smooth base. It's a little bit more difficult to say that this applies over an arbitrary base, but we do have a solid computation that shows that this holds over generic base. So these are some results that one gets from applying these combinations of methods. But I'd like to ask if there's something more we can do here, because in some sense the result is perhaps not totally satisfying, in the sense that we're still forced to go through this the procedure of resolving the geometry and inferring the chiral spectrum from the resolved geometry, and then using this result to understand something about the singular geometry, which is really the vacuum that we're interested in describing. So a question one could ask is there a clear geometric interpretation that's independent of the choice of X? And just to give a motivation for this question, you might take a closer look at the results for the tape models. In that case, all of the chiral indices could be expressed as a triple intersection of particular combination of classes that appeared in the Weierstrass model. So sigma here is the class of the divisor, sigma equals 0, where the 7 branes are wrapped in the F-theory model. And then there's these other combinations of classes associated to parameters appearing inside of the tape model with a particular tuning. And you can view this as counting a number of special points that appear inside of the base. It's very tempting to compare this expression to geometric expressions for the numbers of hypermultiplets in 60 F-theory compactifications. They look quite similar. And they're understood now to count particular numbers of points appearing in a codimension 2 component of the singular, the discriminant locus of the Weierstrass model. So this is a particularly simple example If we ask for more complicated setups, for example, product gauge groups, U1s, rather than getting a simple formula like this, we get something that's a bit more complicated, but it can still be interpreted as a linear combination of collections of points. So one of the interesting things that has emerged in our exploration of various F-theory flux vacua, vertical flux vacua, is the possibility of an actual resolution independent geometric structure. So, and this came about by, this became clear by thinking about the problem from a slightly different mathematical perspective than appears to be usual in the literature.
Sorry, Patrick, just so that you know, you have 5 more minutes.
Okay. So let me just say very quickly what the structure is and tell you the punchline. So consider the lattice of 4 cycles lambda. That's a lattice of 4 cycles di intersection dj. And they have some integral pairing, which is really just a way of reformulating the quadruple intersection. In this way of formulating the problem, the Poincare dual of a flux G4 can be viewed as a vector and sitting inside of this lattice. And we conjecture that this lattice is actually resolution independent. That is to say, if we have 2 resolutions, x and x prime, and we choose bases such that we can sort of strip off the null space, the degenerate part of this lattice, and just focus on the non-degenerate pairing that exists inside of M, there's an integer invertible matrix U such that you can do a change of basis from one to the other, and you get back the same object between any pair of resolutions. So it turns out that this non-degenerate part sublattice is isomorphic to the vertical homology subgroup H2, 2. There's various types of evidence in support of this conjecture. One of them, obviously, is various examples where we've explicitly constructed the change of basis. In the interest of time, I won't have much to, unfortunately, can't say too much about some of the other pieces of evidence, but another one is that if we look at specifically the Tate models, we can find an almost complete general specification of what the non-degenerate, the restriction of the intersection pairing to the non-degenerate sublattice looks like. And combined with some facts about the low energy effective gauge theory, there's enough structure to actually work out an ansatz for what U is supposed to look like, the change of basis. More generally, you could ask about the rank and the signature of M, and they seem to be resolution independent. The rank of M is equal to the number of independent chiral indices. So for example, in the standard model construction, there's 3 independent ones. And the signature is perhaps a little bit less understood physically, but possibly may be related to a topological invariant of oriented manifolds with real dimension divisible by 4. So there's some interesting mathematical results on this kind of invariant related to the Hertzebruch signature theorem. But this unfortunately isn't enough to show that U is an integer change of basis, only that there exists a real change of basis between these intersection pairings. So I'm just about out of time here. Maybe one other thing that I'll emphasize is that what we're seeing is that the space of chiral indices, which are believed to be resolution independent in the sense that they're an intrinsic property of the F-theory vacuum, there's actually more structure here potentially that lifts through this sort of diagram that I have depicting various sublattices that one can go to when calculating the space of chiral indices and the relationship to this lattice lambda. So somehow there seems to be some structure that is actually independent of the requirement that one preserves 4D gauge symmetry that is nonetheless also independent of resolution. So looking ahead, I think I'm just about out of time here. Let me wrap up very quickly. Looking ahead, I think it would be very interesting and useful to rigorously prove the resolution independence of this lattice. It could be useful for several future research directions. One of them is a possible intrinsic definition of the vertical cohomology subgroup in the singular F-theory limit. There's also the possibility of interpreting the chiral indices as counting special points in the base. And this would potentially lend itself towards a computation of chiral indices directly in the singular limit without the need to go through the process of resolving the singular geometry. And finally, it's known and has been pointed out in literature that for pairs of Calabi-Yau, elliptic Calabi-Yau, which are mirror dual to one another, the vertical cohomology of a Calabi-Yau X, which is mirror dual to Calabi-Yau Y, computes, it's equal to, or isomorphic, I should say, to the horizontal component of the 2,2 cohomology in the mirror case. So one might ask and speculate if it's true that the vertical cohomology is invariant over a subset of the Kähler moduli space. Is it also true that the mirror statement, is the mirror statement also true, namely that the horizontal cohomology, 2,2 cohomology subgroup is invariant over some subset of complex moduli space for complex deformations for some mirror Calabi-Yau Y. And if this is possible, it may give a handle on getting a more complete picture of flux backgrounds in F-theory compactifications, where we not only compute the vertical cohomology, but we also compute the horizontal cohomology. So I think I'm just about out of time here. I'll stop. Thank you very much.
Thank you, Patrick, for this well-timed presentation. Are there any questions? Yeah, Lara?
I have a quick one. Really nice talk. I was curious whether you guys see any role in H21 of the fourfold in any of the examples that you looked at?
We haven't really looked, we haven't focused on H21. Is there a particular role that you had in mind for?
So within the context of head-F duality in 4 dimensions, from the heterotic side, you expect there to be sort of 2 components to the flux specification. The discrete part, which is the H22, specifically vertical in that context that you guys are looking at. And then there can also be continuous parameters that would be turning up in H21. And it may be that those aren't there for the class of bases that you looked at, but I was just curious because that structure should also play a role in some examples.
I see. Yeah, we haven't, we've really focused on the vertical cohomology, but it could be that there's an interesting role in interplay between the two. So I'll keep that in mind. It could provide an interesting future avenue. Thank you for the question.
Jonathan?
Thanks. Thanks for the talk. So since you're remaining kind of at the singular locus, you might imagine there could be things hiding there like T-branes. And those can sometimes impact the what you read for the matter spectrum. So how does that or how does that taken into account in the setup you have?
I think probably what I've said doesn't necessarily come into contact with T-branes, because in principle all the computations that I've described here could be done at some generic point in the Kähler moduli space. And correct me if I'm wrong, but my understanding is that the T-brane data really shows up at special subloci.
I see. So maybe, well, this might involve connecting with Lara's question. You also need to specify data about the intermediate Jacobian and how that moves back towards the singular point. Okay.
I see. Yeah, we haven't taken it into account directly.
Well, I guess though that's more on the smoothing deformation side. Anyway, okay, I'll think about it. All right, thanks.
I might just chime in quickly. I think you don't have to turn on T-branes. I mean, in some sense, what we're looking at here is what you get if you turn on vertical fluxes, and there might also be structure you could add if you added T-branes, but we're not necessarily considering that.
No, I understand. It's kind of something you might want to flip on or off. The question is whether there's an ambiguity in the geometry, which needs additional data to be specified. That's more my question here. Okay.
Miriam?
Just a bit of a comment. Since you emphasized a number of times the standard model constructions with 3 families, these global models were really constructed with Jim, Halverson, Ling, Nguyen Liu, and Jiwa Tian. And they lead to to this huge class of globally consistent 3 family models. And that also brings me actually to the complicated issue of quantization of these vertical classes that see it in this vertical middle cohomology that you also connected to mirror symmetry. That seems to be potentially the only way to determine the quantization condition associated with the properly quantized basis of this middle cohomology via mirror symmetry. For 3 family models in the standard model constructions, that actually led us to fractional powers of line bundles, right? And this also further led us to the issues of determining the full-fledged spectrum, not just the chiral index, to be related to so-called root bundles that I may have a chance to talk about on Friday. mainly just comments on this issue.
I see. Thank you. I'll be sure to tune into your talk because I'd like to learn more about these root bundles and such. I am aware of the paper, so thank you for bringing up the connection.
Okay, thank you.
Are there any other questions? Okay, maybe can I just make a brief comment since there's about 10 seconds time left. So the point you raised on your summary sheet about the points in terms of special points in the base that you're counting that corresponds to the chirality. There's actually a nice set of works by Timo and Martin and Christoph who give a precise interpretation or give a precise derivation of this counting of points by constructing essentially the fluxes as matter surfaces. So then the natural way you compute these chiralities are intersecting matter surfaces, which of course intersect over points, and actually the Yukawa points. So there is actually, so you might want to have a look into those papers to
Yeah, I'd like to I'm aware that the time is short, so maybe I won't say too much. Thank you for the comment. I have to admit, a little bit confused about the connection to Yukawas. I think for U1s, perhaps I understand a bit better, but if you look at some of these formulas, for example, it's tempting to try and interpret them as counting the number of Yukawa points, but I don't think the interpretation is quite precise here.
Well, I guess we can move this
ambiguity.
We can move this to the Slack discussion, but so thanks again very much, Patrick, for the nice